Hello everyone, I'm happy to see every one of you and thank you for coming. I will speak about some challenges that can arise in Bayesian modeling, in particular about empirical determinacy and sensitivity. I'm sure most of you have heard a famous expression by a well-known mathematician, George Box, who said that all models are wrong, but some are useful. And he also said that since all models are wrong, the scientist must be alert to what is importantly wrong. And the main goal of this project I'm going to present now is to alert the scientists about the wrong models they feed in Bayesian analysis. I will start with some basic notation. In classical statistics, we assume y1 and yn observations from the random variable y with density function f. In order to estimate the fixed parameter theta, we optimize the likelihood function. However, in the Bayesian inference, this fixed theta parameter is not fixed anymore, but it's assumed to be random. And we have to assume that this random parameter follows to some distribution. In Bayesian inference, it's called a prior distribution. And what we do here, we have to estimate the theta parameter, which is random now. So we have to estimate the distribution of the theta, given the data y, which is called the posterior distribution. We are doing so by using the Bayes theorem, which says that the posterior is proportional to the likelihood times the prior that we assume. And I will continue with some motivation. The two main challenges that arise in the Bayesian modeling are the sensitivity and the lack of empirical determinacy. The lack of empirical determinacy in the sense that the parameters, the posterior, cannot be learned from the data. It can happen sometimes that the posterior is not dependent, is not affected by the likelihood. It is important to know that when we assume a prior or we have a data, what will happen with the posterior when we perturb the prior or the data a little bit, which is not known until now. About the non-identification and non-empirical determinacy in classical statistics, Gustafsson said that Gustafsson defines the non-identification as the violation of the root n rule, which says that the width of the confidence interval is proportional to 1 over square root of n. This means that when we have more data, we have larger sample, we have a narrower confidence interval if the model is identified. And vice versa, if we have a smaller sample size, we have wider confidence interval. But it can happen that we have more data, but the parameter doesn't get, the confidence interval of the parameter doesn't get narrower because it is not impacted by the data. So we want to find these problems in the Bayesian hierarchical models. It is challenging in Bayesian modeling because, for example, in the classical statistics, if you have such problems of non-identification, you get convergence problems and you cannot estimate the parameter theta usually in the applications. However, in the Bayesian analysis, because of the prior assumptions, you may get an estimation of the theta without knowing that it's not impacted by the data, but it only depends on the assumed prior. So we will try to clarify this problem and to find out how the data impacts the spread or the location of the posterior distribution. For doing so, we change the sample size. We assume we have more sample, more data or less, and we will check what happens with the posterior. There are several other works in the literature who are doing similar work. In particular, I want to mention the data cloning by Lele and others who take the same data and clone it, repeat it 2-3 times, and use the cloned data as like original data. This is a good approach, but it doesn't work very well for smaller sample sizes. For example, if you have only 2 data points, you clone it, you don't gain much information. Another work is the scaling, which is also done by myself and my co-authors. But this is also, in this project, we also changed the sample size, but in a different way, where we scale a particular parameter in the Bayesian meta-analysis hierarchical, normal hierarchical model. We scale the within study standard deviation, which mimics change of the sample size. This approach also works, but it's not general. It only applies to the meta-analysis models. And for we try to go for more general approach, which I'm going to present now. This is a paper, a recent version will be available in the Bayesian Analysis Journal in coming weeks. But if you need more details, you can read the archive version of this paper. There is also a package called ED for BHM, Empirical Determinacy for Bayesian Hierarchical Models, which is available on my GitHub page, and it allows you to apply this approach for Bayesian hierarchical models. And this is written in R, not Python. So how do we change the sample size here for, so that it can be applied for more general problems and models? We weight the likelihood. For example, in a latent Gaussian model, the posterior from the base parameter, 1 here means for the base parameter where the weighting parameter is 1, the posterior distribution for the base non-weighted model is equal to the likelihood times the latent field times the prior. It's proportional. And what we do, we just raise the likelihood to the power of W and try to calculate the weighted posterior from this model already. This W is a value close to 1. It's like 1 plus or minus delta. And it mimics upsampling or downsampling. For example, when W is bigger than 1, it means that we give more weight to the likelihood. And when W is smaller than 1, it gives less weight to the likelihood. So when we have the posterior from the base model and the posterior from the weighted model, we want to see what happened, what's the difference between these two after weighting. For doing so, we choose the Bacterial coefficient, which is a metric that measures the overlap between two distributions, in our case, between the base and weighted posterior distributions, and it is related to the proper distance between distributions, Heilinger distance, with this relation. We assume that we have exponential family distributions in such models. This means that it is possible to approximate these distributions with a normal distribution. And for normal distributions, Bacterial coefficient between two normal distributions is possible to get in a closed form with corresponding expectations and standard deviations. It has this form. And so the Bacterial coefficient between the base and weighted posteriors is approximated with the Bacterial coefficient between their normal approximations. So this is the main measure we define. We call it total empirical determinacy, which is defined to be the negative second derivative of the Bacterial coefficient with respect to the weighted factor W. The second derivative of such divergence measures is a common way to quantify the change after some perturbations, to change in distributions. And the minus sign is there to have a relation between the proper density h squared, Hellinger distance. So we have some computational issues. We need to approximate the second derivative of the Bacterial coefficient between the normal, the posterior distributions, and we are using the central difference formula to approximate the second order derivative. So with this, I will go back to the TED formula. With this, we can understand what happens, what changes the posterior distributions, what happens if we weight the likelihood, how the posterior changes. But what is more interesting is to understand how the location or spread parameter change in the posterior distribution. So I can recall here the Bacterial coefficient between two normal distributions, which has this nice form, and we divide it between two parts. We call it BCL and BCS. BCL is the Bacterial coefficient between the locations. It is a common known distance, Mahalanobis distance, and the second product is the BCS, which is connected to the standard deviations. So the BCL will quantify the change in locations, and the BCS will quantify the change in standard deviations. Similar to the TED measure, we define EDL and EDS completely in the same way, like the negative second derivative of Bacterial coefficient for the location and the negative second derivative of the Bacterial coefficient for the spread. And these nice formulas allows us to derive a very useful formulation where TED, the total empirical determinacy for a parameter, is equal to the empirical determinacy for location plus the empirical determinacy of spread. And this allows us to understand to which proportion of the total change is due to the change in location and which proportion is due to the change in spread. So for implementations, I will introduce the software we have used. We have applied two known techniques, MCMC sampling and approximate posterior by nested Laplace approximations. For the MCMC sampling, there are two very known softwares. The first is JAX, developed by Professor Martin Plummer, who is a co-author of this paper. And there is a package that allows us to work with JAX from the R environment. The second software is called STAN, which is developed by Professor Andrew Gelman and his team. And there is also a nice package developed by, again, Martin Plummer, which allows us to do diagnostic and convergence checks of the MCMC samples after the estimation. Another way to approximate posteriors is a numerical method by Professor Rue, who is also co-author of this paper. So how we do the weighting, how we handle the weighting in these programs. In INLA, it's easy because INLA is very fast. For such small models, it runs in seconds. So it's not a problem to run INLA several times. There is a nice argument in INLA which is called weights. For the normal base model, the weights argument is equal to 1. And for getting a weighted likelihood, we just need to change the value of the W to 1 minus delta or 1 plus delta, and we rerun the model 2 more times in order to estimate the central difference of the Bacterial coefficient, the second order derivative of Bacterial coefficient. In MCMC-based algorithms, it is a little challenging. For JAX, for example, We don't want to run this model several times because they took much longer. For JAX, we have derived the formula where the weighted posterior is proportional to the likelihood raised to some power times the base samples of the posterior. And the likelihood samples from the first JAX call can be derived from the deviance statistics, which has this expression. And so we get the samples of the weighted posterior. And for STAN, it's even more challenging, I would say, because you cannot extract the likelihood samples. But it's easier to generate a quantity, the likelihood samples, during the call of the STAN of the model. After having the weighted posterior samples, we need to estimate the expectation and the standard deviation for the weighted posterior samples with these formulas. And it is always good to equip the Monte Carlo estimates with Monte Carlo standard errors. For doing so, assume we have an MCMC sample that explores our posterior of length m. And for each statistic of interest, for each quantity we want to compute, we generate bootstrap samples and we calculate the statistics of interest. And then the standard errors for each statistic can be calculated with this formula. I already talked about the R package, which works with all of these estimation techniques. And now I want to move to the applications. The first, I will focus on a challenging data set where we have complete separation in the data. What is a complete separation? In a very simple case for a binary data, it occurs when one exploratory variable predicts the outcome perfectly. In such a case, for example, in a 2-to table, we will have zeros for these observed frequencies. And it will cause a numerical problem when estimating the parameters for a logistic regression. So for this challenging data set, we know that we have identification and determinacy problems, so we will challenge our method to see if we can capture this problem with our measure. So I will introduce 3 examples, a normal example and 2 Bayesian logistic regressions with separation data. The first one is a simple example. It's just to show how the model works. We assume we have n equal to 10 observations of y, and we have the sample mean, variance, and the precision, and we from the simulation study, and we assume a very basic normal model for the observations y with mu expectation and precision kappa, and we have to assume a prior distribution on the expectation parameter m with some hyperparameters for the prior distribution. For such a simple model, it is possible to derive our measures also analytically. And in this table, I show the results from analytical calculations in JAX, and you can see that they match perfectly. And this is not very informative because we have only one parameter in this simple model, but we already can see that the proportion of changing the spread of the posterior is 1 compared to the change of the location, which means that this parameter is determined by the data, is well determined by the data. So when we weight this data, this parameter will be informed. The second application I want to present is about Bayesian logistic regressions on a data with complete separation. I think most of you are most of you know the logistic regression, and this is only the Bayesian case of it, where we assume priors on the intercept and the slope parameters. There is a paper that recommends this specific priors with prior parameters for analysis of data with separation. So the first data set with complete separation is from bacterial resistance data. They had some strains of Escherichia coli bacteria isolates. We got this data set from the Medical Microbiology Institute from the University of Zurich, where they have two different types of bacteria, resistant and susceptible. Resistant means that if you put an antibiotic on this bacteria, the bacteria will not be dead. And susceptible means that the bacteria will die with the given antibiotic. So after an antimicrobial susceptibility testing, which is the following, I will try to describe it shortly. So they have some discs, they brush the bacteria on it, and they put an antibiotic in the middle of it, and they put these plates in an incubation phase. After, I think, like 8 hours, they measure the diameter of, around the antibiotic, the diameter of all the bacteria that are dead because of the antibiotic. It can be different because the bacteria are different. They might not die, or they might be dead. And this diameter is called inhibition zone diameter, which has values between 6 and 40 millimeters. 6 is because of the diameter of the antibiotic in the middle. So they cannot they cannot measure the values that are smaller than 6. And we have 3 different experiments, one with 3 different antibiotics, one with imipenem, amoxicillin, and ceftriaxone. So you can see that we have 3 different positions of the data, where the black bars show the resistant bacteria and the gray ones are the susceptible. You can see that we have an overlap of resistant and susceptible bacteria. We have quasi-separation and we have complete separation. So we have applied our methodology on all these 3 types and to see whether we get problems in the separation case. I have a table here with some results. The numbers are maybe a bit smaller, but I will try to describe. All these values are here in order to just see that they agree between the methods and parameters. What is important here is the total empirical determinacy of all the intercept and slope parameters for all 3 data sets. We can see that again, the empirical determinacy measure also agrees between the methods. And what is even more interesting is the proportions of the change in location and spread of the posterior distribution. I will recall that for the first data set we had overlap, and we have the PEDS, the change in spread, equal to 1, which means that these parameters, alpha and beta, are determined by the data. For the amoxicillin, we have quasi-complete separation, and we already see that the change in the posterior is not only due to the change in spread, but also due to the change in location. And for the ceftriaxone, where we have complete separation, we already see that the spread doesn't change much when we weight the likelihood. This means that these parameters in this model for this data set are not well determined by this data. We did a simple experiment. I will go back to this data pictures again. We took the first data set with imipenem, where we have two overlaps of the resistant and susceptible bacteria, and we shifted the resistant ones, the black bars, to the left one by one in order to simulate different separation rates in the data set. So we got 20 different data sets with 20 different stages of the separation. And we applied the techniques to all these 20 data sets. In this first figure, we plot the total empirical determinacy, and on the last one, we plot the proportional empirical determinacy of location and spread for both data sets and both methods. I will focus on the second plot here. This is more interesting. So we can see that the proportion of the location is close to 0 when the separation is small, and it goes up to 1 when the separation rate increases. And similarly for the spread, proportion of the change in the spread it starts with 1 and goes down close to 0 as the separation rate increases. And this is another application of hemophilia A gene. This is a disease. In this data set, we have 52 observations. 22 of them are carriers of hemophilia, and 30 are non-carriers. This is a similar application, only that here we have two covariates, X1 and X2, and we apply this model to the data set. And you can see the separation line, so we again have a separation problem. And the empirical determinacy measures are shown here. Again, for the TED, the values, it's interesting that for the intercept, the TED value is smaller and it is larger for the slope parameters. And this behavior remains for all three methods. And most importantly, the proportional measures of change in location and change in spread. We can see that the proportion of change in spread is much larger than the one in location. And this is also an alert that there might be a problem, and we know the problem is the complete separation. So there are some limitations of this methodology and further works where we want to choose the delta for weighting the likelihood in a more clever way, probably. We could modify the method to cope with integer rates, for example, and this will be comparable with the cloning method I showed at the beginning. And at the moment, our method is based on the mean and standard deviation on the descriptive statistics for the location and spread. But it would be good to have a measure that is, for example, based on the quantiles to have more stable results. And some strengths of this method. For MCMC techniques, we have developed a fast computation method in order to not run the JAX several times. The estimates of the empirical determinacy are equipped with the standard errors, and what is the most important is that the refined method where we look at the proportions of change of the total impact of the likelihood allows us to understand how the location or how the spread is changing. And this method is already applicable to more general outcomes, not only normal or binary. And these are some references we referred in the manuscript. And thank you very much for being here, and I'm happy to take some questions and remarks.
Thank you for the great presentation. One question related to the choice of the prior in your study. So it seems you use only normal.
Yes.
What if you change the priors and how the result can change? Do you have some exercise on that?
Not in this paper, actually, with these applications, because we have chosen, I will go to the models first. Not here, sorry. Yes, for example, here, as I said, we have chosen priors that is recommended by quotient others that is specific for such data set where we have separation. But for this application, we didn't try other priors because we have similar applications in another paper where we quantify the sensitivity of the change in prior. So, but with other applications, not on this data set. So here I don't know what will happen. We just have used the recommended priors. The goal was to understand the impact of the perturbations of the likelihood here. But that's a valid question. It's interesting. Thank you.
I have a 1 or 2 part question depending on the first part. So is it ever the case that the scale parameter of your posterior, I guess, which is what you're trying to determine, would be larger than the prior? That is, can you not simply determine or measure determinacy as how much the posterior scale is smaller than the prior scale?
You mean the posterior, by posterior scale, you mean probably the TD, what we computed, or it's something, so the change in the posterior already? Or you mean the weighting part?
Of the scale parameter of the posterior distribution.
So can you repeat the question?
So is it ever the case that the posterior variance of your parameter is smaller than the prior variance? Or I'm sorry, is larger than the prior variance? I guess I'm just wondering, can you merely measure determinacy as whether the posterior variance is smaller than the prior variance?
Oh, I got the question, but I don't know how much the prior variance has to do with the change in the likelihood. Because when we want to understand if the parameter is data determined, we are working with the posterior, but the change in the prior is already the sensitivity part, right? And
I guess I'm wondering if, without any data, if you set the weight on the data to 0, the likelihood to 0, then the posterior would be exactly the prior.
Yeah.
If you set the weight to 1, then the posterior will hopefully be different from the prior. I would think that it would only be smaller, and
it's a difficult question. I don't know. We didn't think about the prior scale in this method.
Okay, I guess I have one other different question. This reminds me a little bit about of the bootstrap or the jackknife. And the bootstrap, for example, instead of scaling the likelihood, it randomly scales the likelihood. And I would think that if the posterior happens to completely, or if the distribution completely matches the prior, then it might appear that there's no determinacy. But if instead of that weight factor, you're choosing a single weight factor, but if you randomized it a little bit, you might get better precision. Have you thought about the
That's a good question, yes. We thought yes, randomization would be a good extension. We thought to change the weight to have integers or to have some clever way to choose it. But also, yes, randomization would be also, we didn't work with it, but we had this idea from a reviewer whether this can be considered as a random parameter in the model. We didn't work on it yet, but it's a good extension and would be interesting to know. Thank you for the questions.